Welcome, everybody, to our next Thursday Work from Home webinar. Today, we'll be continuing our discussion about Hull-Propeller Interaction, focusing today on propeller performance. Last webinar, we talked about the wake field and how the ship influences the velocities that the propeller sees, and we'll then continue with the uh, sort of the discussion about how a propeller functions within the wake field itself. Just a few administrative notes. This webinar is recorded. You'll be receiving a follow-up email with a link to the recording so you can view it again and share with colleagues. If you'd like to pose a question to me, you can use the attendee chat or the ask the presenter a question. And if we have some time at the end, I'll try to field some of those questions for you. So let's get right into it. Those of you who have shared webinars with us over the past year have seen this graphic frequently, so I'm going to continue to use it again. What we're looking at is to sort of discuss the propeller performance behind the ship. You'll hear or read terms like behind the ship or on the ship as a way to describe a difference from an open water case, which we'll describe a little bit later. But what we're doing here is really describing how the existence of a ship and upstream structure and downstream structure, like a rudder, actually affects what the propeller sees and its overall performance. Now, just a review kind of from part one. Actually, this whole discussion started 2 webinars ago where we did one on propeller-driven noise. And one of the comments there was about how the inflow to the propeller is one of the best ways of reducing noise. And we'll see how that works its way out. That led to this part 1 on wake fields, where a propeller sees the term a wake field. That's the velocity distribution. We can use this image in the center there, the colored contour plot, as a way to describe velocities, high velocities in the reddish colors, away from the stern shape. This is a single screw merchant ship, more in the free stream velocities. And then up in the top dead center near 12 o'clock, we have the slowest velocities because of the existence of the ship stern structure and the shafting and all. Now, there are 3 types of wake fields that we discuss: nominally effective and total. And any discussion about propeller performance, we're talking about effective wake fields. So I'll refer you to that first webinar for any additional discussion about that. But we broke up our wake field into radial and circumferential parameters. So what we do is we take the full propeller disk, all the velocities, and we take a cut. And I'm using the 80% radius cut here as an example. That gets turned into a circumferential plot where we see the velocities at each theta or circumferential angle position, and we get a peak at the top, a peak wake fraction, high wake fraction, low velocities, and then low wake fraction, high velocities down at the outer angles. From that line plot at that 80% radius, we then integrate and solve for an average velocity. And then when we look at the average velocities radially, or the average wake fractions radially, we get the plot at the bottom. So we go from the full disk, we break that up into radial cuts, and then we display those radial cuts as circumferential lines, find an average for those, and then we get what's called a circumferentially averaged wake fraction or velocities. Now we'll see how each of these are used in the propeller performance. But this is just kind of a reboot about the wake fields. Of course, as I said, I'll refer you to the last webinar for additional details on this. Now, some key pieces of propeller performance here that we need to talk about, and that has to do with a velocity helix. Blade sections like this little yellow-orange section here that kind of represents that 80% radius position, that section flies along a helical path. And we're going to think of this as a short stubby airplane wing, if you will, that has a shape to it. It has an angle of attack along a path. Well, the path is not linear. The path is a helix. And that helix is defined by the RPM plus the advanced velocity of the ship that gives axial and tangential inflow velocities. Now, these velocities, they can locally vary by radius from root up to tip and its circumferential position, as we saw from the previous plot here. It varies, you know, different rotational positions. So we'll use the symbol theta for that. You'll see that used herein. So what we have is a format, a structure for describing the path of the propeller blade section as as flight along this particular helix. Now there's two different uh, approaches or two different pieces to this when we talk about performance against a section helix. One is the mean velocity that we described in the last slide. And so that leads us to what we call a steady calculation or a steady performance, and that's uniform around its rotation. Well, that's kind of a fictional performance, but it's an absolute necessary approach, just given the computational complexity of full wake field calculations. We always do design based on steady calculations, and we can do an awful lot of the heavy lifting of propeller performance using steady calculations and evaluating steady performance. Now, unsteady performance is in the non-uniformity of the helix, the variation in the wake field itself. So we'll touch on both of those things here. First, we'll talk about steady performance, and that's really performance without a wake field, and by that I mean without circumferential variation. Now, it's a true helix. It's uniform across its entire rotation. And if it's also radially uniform, which means all the velocities are the same around the rotation and the same from root to tip, we get a constant velocity case, and that's what's termed the open water case. And we would only see that in model tests, for example, of propellers with no shaft angle. It's what all of the series propellers, B series gone, all of the propeller series that we've come to know, they are based on an open water steady case. Now, in this case, the foil section, that 80% yellow section, flies at a consistent angle of attack. It's unchanging throughout its rotation. So the lift and drag on the blade section are uniform and the same throughout the rotation, and there's no variation in thrust or torque on the blades by any rotational or circumferential position in this. When we get to unsteady performance, the path is no longer a true helix. It deviates from that mean steady helix. We can almost think of this as a helix segment. And I'm using this red band here is to illustrate a couple points. If we have a part of our velocity that's slower, like the top dead center piece that we saw in the wake field, we can think of that as a compression of the helix. Higher velocity is a lengthening of the helix. So in low velocity areas, this blue helix line that we see actually becomes more vertical, more up and down. The blade section then flies at a higher angle of attack. The opposite is true with high velocity cases, where now the helix is expanded, the angle of attack goes down, and it's even possible to have cases where you get into a negative angle of attack. And there's performance issues that becomes a very critical design point. We'll talk about that a little bit later as well. So what this means is that the lift and drag will also change with the changing angle of attack into the flight. Different blade loadings, different kind of pressures, different impulses as it rotates around inside the wake field. Now, as we want to drill down into the actual performance on the blade sections, another key piece of this is that the velocity also varies chordwise. It's no longer uniform from tip to tail, or from nose to tail, leading edge to trailing edge. So we actually have a distribution and a variation in the velocity across the section length as well. So when we're doing performance predictions, calculations of a propeller in a wake field, there's a couple different approaches we can take to try and approach or determine what the unsteady performance is. Remember, we had the steady mean performance. Now we're looking at the unsteady performance. The first is what's called quasi-steady. That really is just a snapshot of what would the steady performance look like at this position with these local velocities. And actually, quasi-steady calculations can do a really good job at predicting a majority of the unsteady um, characteristics, the changes in thrust loading, the changes in lift and drag, all of the things that are important to us as they relate to unsteady performance, the development of impulse pressures for the generation of noise, cavitation, all of those kind of characteristics. But let's kind of drill down into the physics of this and see if we can understand a little bit more about what's happening. The unsteady calculations, the real unsteady performance has to account for not just the position of the change in velocity, but the transient variation. How quickly does the propeller blade pass through a region of changing velocity? That's one thing that the quasi-steady snapshot really is not able to fulfill. And also, we have vortices that remain in the water, in the wake, that do affect trailing blades. And two different computational approaches that are often used. The first of which is called a flapping foil. If we come back to this here, you can kind of envision the idea that as the blade rotates and it sees inflow at different angles of attack, that's the equivalent of a foil pitching up and down. And so there's a flapping foil methodology that uses angle of attack to solve for this. But then there's a gust or a parallel shift method. Let me try and have you visualize sort of what happens here with these vortices. And the best illustration I could think of was a paddle in a canoe or a kayak. We've all been out in a paddled boat, and if we take our paddle and we put it in the water and we pull it towards us, what we see is that there are vortices that are shed from both sides of the foil. And if we were to set our paddle in the water and we rotated it, we would see similar vortices coming from the leading edge and the trailing edge. Now, if we turn our paddle and align it with our our canoe or our kayak, and then we move it side to side or twist it. That's really what we see with these two models, with the flapping foil or a gust model being a parallel shift of our paddle. And we can use either of those models to take the change in velocity from that mean, the change of that inflow direction, and we can convert that into aligned velocities and perpendicular velocities in the gust model, or changes in angle of attack in the flapping foil model. And one of the other pieces of unsteady calculations is we need to use an appropriate velocity. Now we can see from the illustration here that the blade at top dead center is passing through a pretty tight transition of velocities. So the leading edge, the mid chord, and the trailing edge are actually seeing velocities um, at different magnitudes. So what is a local mean velocity that we might use for an unsteady calculation? Well, a couple key takeaways or things to think about is the forward half of a propeller or any airfoil does most of the work. You know, um, one of the attributes of foils is that the center of motion, or the center of forces, is at the 1/4 chord length. Now that's an approximation based on characteristics of different foil shapes, but it goes to show that the forward half and the velocities associated with the forward half are most important. So it's not just a matter of taking an average. It's not just a matter of doing a snapshot on what's called the blade center line. You actually have to think a little bit more about how the foils function in order to determine an appropriate averaged velocity, chordwise averaged velocity. So as we take this idea of a mean steady um, a computation, we'll use that for design. Unsteady calculations are not very design friendly because design is an iterative process. And we're designing for the whole propeller, not just evaluating what one blade does at one position, which is the real key of the unsteady calculations. So we use what's called wake adapted propeller design. And quite simply, that's a blade design that's adapted to the mean inflow. Now, this, of course, can be a custom design for a ship's wake field, like the one that we started with, but it does not necessarily need to be that. An example of a semi-custom approach, let's call it, is the B series that we all know. The four-blade B series has a pitch reduction into the hub or into the root, starting with the 60% radius down into the 20% radius at the hub. There's an 80% pitch reduction in that region. And that's simply a tip of the hat to the fact that boundary layers, like we see in the upper right, near the shafting and the strut bossing, is always going to slow the water down before it gets to the propeller. So velocities near the hub are always going to be slower. So we want to adapt or design adapt the pitch to that slower velocity. And that is shown in this pitch reduction. Now, this becomes a product model characteristic, a semi-custom that can be wake adapted for a particular ship type or a propeller model objective. Another example of this for high speed or high performance motor yachts, for example, is that we're seeing many of these semi-custom stock models have a pitch reduction at the tip. That's to relieve a little bit of the loading and the pressure pulses that would translate into interior noise and vibration. They're high powered, they're high speed. There's a lot of thrust being developed, but we can use this as a product model characteristic, wake adapted, for that particular type of application. Now, wake adapted propeller design is the second step of propeller sizing selection and a design. It's the start of the component design of the propeller or the detail design. The first step is the principal parameters evaluation in a tool like NavCAD, where we're looking for diameter, pitch, blade area ratio, shaft RPM. Those are the key pieces of this. Optimized for thrust torque performance, acceptable blade area for cavitation. But of course, it doesn't take into account radial differentiations or circumferential differentiation. So the next step is this wake adapted design, and we would use a tool like Prop Elements for that, where it's a steady calculation based on the circumferential averaged effective axial wake. Optionally, we can also include tangential wake at that point. Now, as mentioned, this is a steady calculation, but its objective is the design of radially varying characteristics, pitch and camber for principally for thrust and power loading efficiency and uh, shockless entry, it's called, for the shape of the camber to minimize pressure peaks at the nose for cavitation assessment, but then chord and thickness for strength calculations, sufficient blade area, again, for camber and blade pressures. So the difference is between a wake adapted propeller and true unsteady performance. We need to account for those in different ways. Now, an interesting an interesting characteristic is that a mean steady state thrust prediction and a true unsteady thrust calculation in a wake field tends to be very similar, and, quite comparable. The difference is in the torque and the power. And if we think about the unsteady calculations as variations in angle of attack, a flapping foil, what we get is a little bit more thrust when the angle of attack is high, a little bit less thrust when the angle of attack is low. So the thrust balances out, but that variation is an increase in drag in each direction. So the torque is going to be different. And it's this unsteady case behind the ship power and torque differential that's really the basis for the relative rotative efficiency, the third of our Hull-Propulser interaction coefficients. Now, pitch in a wake adapted steady calculation, is an imperfect compromise. And it's sometimes hard to wrap your head around this notion, but we see for single screw merchant ships, for example, relative rotative efficiency can be slightly more than 1 or 2%. Well, what that means is that our average steady calculation really is a little bit of an off design compromise, and that by bringing some of that back into the lower two-thirds where it's in faster velocities and more uniform, it's actually a little better than the compromise. We have to hit the thrust because that's what moves the ship. So that's where our thrust works out to be. Now, a design tip for anybody designing wake adapted propellers is we tend to bias more towards pitch and less to camber. Remember, lift in any kind of a foil is a function of angle of attack and blade camber or section camber. And so what we want to do is we want to ensure that we avoid any negative angle of attack situations as its rotation, because that can lead to very damaging face cavitation, pressure side cavitation. So we always want to steal a little bit from camber and give it a little more towards pitch. So we always maintain a little bit higher pitch. That's another reason why we're a little bit more off design, a little bit more imperfect on the compromise, and how the relative rotative efficiency can be a little bit more than 1 in certain cases. Now, how do we estimate a wake field when none is available? Wake adapted propeller design is important for us to do as early in the design spiral as possible because it addresses um, key characteristics that is not necessarily fully modeled in our system calculations in a tool like NavCAD. We we want to look at a little bit more about our unsteady calculations and our wake adapted performance to this. Also, we have the ability of using more contemporary foil sections in a wake adapted propeller tool. So, the first step to estimating a wake field, if you don't have model testing, if you don't have full CFD at that point for what the inflow wake fields are going to look like, we predict the wake fraction with NavCAD. That's an effective wake fraction, and we scale that wake fraction to radial wake estimates, through a distribution builder that we have in prop elements. And we've got a handful of vehicle types where you can enter in, for example, a single screw ship, block coefficient, waterplane coefficient, and the effective wake fraction, and it gives you an estimate for the radial wake distribution, the mean wake distribution. Now, it's not perfect for that ship, but it's representative of the family type characteristics of that ship. Same thing for twin screw ships, and we also have axisymmetric submersibles as an option for building an appropriate wake distribution for wake adapted propeller design very early in the design spiral, where you won't have to go to CFD calculations, model testing, or any kind of um, expensive or comprehensive empirical studies. One quick sidebar is that we do also have simple characteristic or simple parametric estimates for some of the characteristics of the circumferential wake distribution, like the wake peak. There's a stern angle that can be used to predict what that wake peak is going to be above mean. So you can do a lot of initial development and get sufficient data for studies on um, unsteady calculations, noise and vibration, the various pressure pulses very early in the design, and have really good um, information about whether a propeller is going to be generating underwater radiated noise, pressure pulses for internal noise and vibration, without prior to having to do any kind of model testing or CFD studies. So let's talk just briefly about self-propulsion calculation with CFD. CFD is becoming much more accessible, and it's used very frequently for hull form modeling, resistance prediction, and the like. But when it comes to propeller calculations with CFD, we have to put a propeller in what's called a rotating frame model. And of course, that's going to fully resolve all of the wake field performance, unsteady, everything is established there. However, the geometry of the propeller is not always available. We don't know what the design propeller is yet when we're doing our hull propulsor studies. Um, that's something that prop elements can generate, is a propeller, after or even prior to the wake adapted calculations, to develop a proxy propeller that can be put on the CFD calculations, much like a model tank would do with pulling a stock propeller off the wall and putting it on a model for self-propulsion um, analysis. Now, also, propeller calculations, full rotating frame propeller calculations, can be a little intimidating, and there's still some skill needed in determining, how much do you rotate the blades for each time step? What kind of grid refinement do I need? What's appropriate in order to model the different kind of characteristics. We already talked about how the leading edge of a foil is more important than the trailing edge. So how can I make that grid more propeller friendly? What do I have to do at the tip? Is there a nozzle involved? So there's a lot of things that can be somewhat intimidating about a rotating frame calculation. I don't want to overstate that. We do it all the time. It's just, it takes a little bit of skill and knowledge and experience to be able to identify things. And having a quantitatively strong tool like prop elements to develop the target benchmarks can be really valuable to help to ensure that your outcomes are appropriate. If you get numbers that are widely different between the two, then you have to sit back and say, is there something about my CAD model? Is there something about my calculations that needs another set of looks? So one of the things that's done frequently is to couple CFD with a propeller code like prop elements for an efficient workflow. And it's the responsibility of the propeller code for the unsteady prediction of performance, which includes the induced velocities, induction, and the calculation of the body forces that are passed back to the CFD tool. One caveat is extracting the inflow on the CFD side can be a bit of a challenge. Where do you put that inflow plane? It can't be at the propeller. It's always a little bit upstream, but how far upstream? Are there corrections needed? Is that inflow plane intersecting a piece of stern structure that's going to disrupt what's really going on, at the propeller? So there's a little bit of skill in setting that up as well. And just a quick note, we've been working with the folks at NUMECA here for some time on coupling prop elements with their fine marine software. We've had really good success with it. We still have a number of small issues to work out. We're doing testing on different hull forms and applications. So we hope to have something ready for users to take a look at and employ in their work, in the second quarter of this year. Um, so just some final thoughts on performance behind the ship. A propeller sees an effective wake field. Sections fly on a helix or helix segments that are created by the inflow and the propeller's RPM. We have steady versus unsteady performance. Unsteady calculations are more complex than the steady because they need to deal with chordwise variation in velocities and also some of the vortices, the shed vortices that are part of the added drag and the flow that gets carried into the wake. We use what's called wake adapted propeller design, which focuses on the radial distribution, the radial mean distribution, but that same tool can be used for full um, quasi-steady and unsteady calculations around the wake field. Prop Elements has that capability, for example, and CFD calculations, full integrated Hull propulsor computations with CFD, can include that rotating frame of a propeller, or the calculations can be enhanced by coupling to propeller codes, similar to how they can be coupled with more simplistic actuator disks. The propeller code becomes a really appropriate and more fully baked proxy of propeller performance in that wake field and wake adapted conditions. So with that, I'd like to thank you all very much for the time this morning. Be happy to entertain a few questions here. Our next webinar will be in April, and the topic, it's a surprise. That simply means we haven't thought of anything yet. If you have anything you'd like to see, give us a shout. Check our various social media links for updates. You'll be receiving emails. But if you have any questions in the meantime, or wanted to discuss the topic a little more, you can reach me at the email shown. Again, this has been recorded, and you'll be receiving a follow-up email with a link to the recording. And let me see if we have any questions here. Uh, wow, okay. Long set of questions here. Do you have a design tip for naval architects? As a propeller designer, what kinds of nominal wake fields do you want to start your propeller design from? I think there's no single magic formula, but do you have a personal preference? Another question is, you raised very good questions about taking the inflow from CFD solutions when the propeller code and the CFD is coupled. Do you have answers to those? Um, wow. Sure. Let's me try and spend just a couple minutes on this here. The difference between wake fields, and let me kind of come back to. Um, Actually, I can use this here. If you remember, we talked about nominal, effective, and total. Now, the propeller needs effective. There's no really good way to measure that in a model test. You can kind of guess at it, but it either has to be determined from a nominal calculation or measurement, where you add the induction effects, the propeller effects, or it's a total calculation and you deduct the induction or the propeller effects. Now, the latter is how we're approaching the coupling with Fine Marine, that they're giving us at an inflow plane a set of total velocity figures. Now, and then prop elements is responsible for taking that total velocity, which includes the propeller effects, figuring out what those are, and then deducting it, subtracting it, to derive an effective wake field. And then that runs the full wake field computation at the effective wake field, and then it returns the body force is equivalent to a particular thrust. And we use an RPM solution to this to kind of match the objective thrust as a part of the calculation. Now, another traditional way of doing it is to take the nominal wake field, which is without the propeller at all, and then use some techniques based on propeller performance to go from nominal to effective. And there's a number of different approaches that have been used in um, the literature. You'll find technical papers on how those methodologies are done. That's not something you can really do with a fully interactive CFD calculation, because a nominal calculation, a nominal wake field, is without the propeller. You can only do that at one velocity, take a snapshot. And so, that's where you would either do that in model testing, do that in CFD, and then try and figure out what the equivalent effective is for that. What we're sort of proposing is, if we can get a decent estimate of an effective wake field distribution, and we go to a system level calculations like NavCAD for the prediction of effective wake fraction, we can scale just a little bit what our estimates are. And so that's how we would do that in the absence of CFD here. Now, um, when we talk about uh, sort of hints or design practices for where to place the inflow plane, or where to capture the inflow velocities. Typically, it's a plane, it's a disk that's upstream of the propeller just a little bit. It needs to be more than a handful of cells in the grid, because there's local shear effects if it's too close to the propeller that we want to avoid, but not too far upstream that we have to correct for the difference, which we can do, but it's just another additional slight uncertainty because you have contraction in the jet stream, and we want to trying to go from an upstream disk area into a propeller disk. You're making estimates on contraction and corrections for the distance, so it wants to be close. And what we've even seen is that it's not a plane. You can actually create a radially varying um, sort of axial position uh, that is just a little bit upstream of where the leading edge of the propeller or the body of the propeller. That's more of a 3D approach to the position of that. It takes some, believe me when I tell you, it takes some trial and error to figure out a methodology that is consistent with this, because you have to allow the calculation on the CFD side to get to some level of not convergence but a consistent velocity. So has that velocity had enough time for the propeller effects to migrate upstream, or is it a really quick snapshot? If it's an immediate snapshot, it almost is a nominal wake fraction. So you have to um, uh, you have to kind of work through this, and that's one of the things that we're hoping to do with NUMECA, for example, and the Fine Marine tool, is to establish some of those practices to make it easier for the naval architect who wants to use that kind of calculation approach. Long answer to your question, but I hope that was useful information. Um, as I don't see any other questions at up here right now, if you have any others, um, pop them uh, to me by email. We'll be happy to follow up. And with that, let me say thanks again, and we'll look for additional information from us on our next webinar. And if you've got a topic that you'd like us to discuss, reach out to us, and we'll see what we could do. With that, let me say thanks again, and we'll see you next time.